Hi everyone. This is a presentation that involves the time value of money, and I suspect at the end of the day it will be between 30 minutes and 60 minutes, but we'll see how it goes. A couple things before we get started for today. One is that you'll see a couple of pictures and diagrams and some references to some formulas, and those come out of the text Corporate Finance, the Focused Approach by Earhart and Brigham. Also, the calculator, the financial calculator that I'm going to be using during this presentation is going to be the Texas Instruments BA2 Plus. Nearly all of them are the same or similar, but that's the one that I'm going to be focusing on. The learning objectives for this session are to be able to recognize different applications that involve the time value of money. And once you recognize those applications, figure out what the drivers are of the problems. And that will involve things like the time horizon, interest rates, the amount of money that's at stake, and whatnot. And then given a set of information, be able to identify what those things are. More importantly, figure out what it is that you're looking for in the process of solving these problems. In the context of a company, just to give you a sense of where this topic fits in sort of an overall picture, finance usually is focused on understanding how value is created. And to understand how value is created is a function of what something costs and what something is expected to bring in given the investment that you're making. And so what we tend to see is finance focusing on what a project or a company's expected future inflows will be. And in finance, we call those free cash flows. And free cash flows, as we'll see in a subsequent presentation, are a function of investments and revenues and costs of a particular project. Also, you have an investment that's made that involves either some form of borrowing or equity from the owners, and those blend together into component costs. And those essentially become the rate of return that we require to be able to achieve on a particular project or company. So the only thing that I think you have to understand from this is that there's a lot of stuff that we have to work on that will come together. The important piece for time value of money is that the inflows and the outflows will be evaluated over a series of months or years, and we have to be able to calibrate what that means to us today. So for example, would you prefer a company that provides you with $10,000 or $20,000? Obviously, it's going to be $20,000, except if I tell you that the first company will provide you with $10,000 in 1 year, and the second company will provide you with $20,000 of return in 10 years. So now the math is a little bit trickier, and most of us might prefer a $10,000 return on our investment in 1 year versus the $20,000 10 years from now. So we need to figure out a way to calibrate investments that occur over periods of time. Those are applications that involve companies and company projects. There are also a bunch of personal finance applications. So personal finance applications are essentially anything that involves time and money. And so if you see the three examples that I am depicting here, one that might involve saving for retirement, and then when you retire, determine how long it will take for you to run out of money, saving for college, and what are the key variables that influence the chance that you'll have enough when your kid goes to school or when you do. And then finally, trying to figure out different deal structures, such as, does it pay to buy or lease a car? Is it better to rent or buy a house? what can you afford in terms of monthly payments, and given different interest rates, what should those monthly payments be? So those are some examples of personal finance applications. The process that you use to solve these types of problems generally fall under a few different kind of generic headlines. One is being able to draw out the timeline properly and identify when the cash comes in or when it's expected to go out along that timeline. And by drawing out the timeline, you can draw it out physically or you can map it out in your head, but it's a good idea to depict that geometrically so that you kind of can comprehend the problem. Maybe not for the simple ones, but for the more complicated ones that we'll see later on. Also, once you draw out the timeline, it's then helpful in determining and identifying the information that you have and what you're looking for. Are you looking for what something is worth later on, or are you looking for what something is worth today? Are you looking for the interest rate that you'll need to achieve in order to save a certain amount, or are you looking for the amount of time it will take to save something? And so that's the process that involves pulling together the information in a problem, dissecting it, translating it into different drivers to be able to solve. There's a lot of notation. There's multiple methods that can be employed to solve these problems. The same as if you're driving from one point to another. There's usually a couple different ways to go, and you'll solve them the most elegant way or sometimes the most effective way that you can. It might not be the fastest, but there are a few different ways to get there, and as long as it works, that can be okay. You'll see different types of notation in different textbooks, different calculators, and whatnot. Don't get bogged down. Just think about the process that you see here in terms of the steps that it will take, and then using that, figure out the method that you want to employ, whether it's using algebra, whether it's using time value of money tables, whether it's using a calculator, or whether it's using Excel. Those are all identical ways or can be used to solve these problems. I'm going to focus on time value of money calculators, and so you'll see some terms in here that are consistent with time value of money calculators. But you can also see that the first thing that I do is take a look at drawing out a timeline. So I'm going to put check marks next to different cash flows. When I'm drawing out the timeline for the examples coming up, sometimes I'll put pluses to denote those are inflows. Sometimes I'll put parentheses or negative signs to denote that those are outflows, just so that it's crystal clear what cash is going in and what cash is going out. Also, the when is important. When do you have money flowing in? When do you have money flowing out? Technically, period 1 encompasses this whole first part of the timeline. But usually when you see timelines depicted in time value of money applications, the tick mark 1 is usually represented at the end of the first time period. 2 would be represented at the end of the second time period. And that's sort of the standard. That's the way that we're going to start for now. But we can change that at any time. As you might suspect, if a cash flow is made at the beginning of the year, that's going to have an impact compared with if it's made at the end of the year or at the end of the period. Similarly, if it's made during the middle, it's going to have yet a third implication. So we just have to start somewhere. So the best place to start is to presume that all cash flows occur at the end of each period. So if I say something occurs at time period 1, it's 1 year from today or 1 month from today. Time period 2 at the end of the second period, time period 3 at the end of the third period. Some other things to get used to. PV in either Excel, your textbook, algebra, or your calculator refers to present value. It's a little bit of a misnomer. Present value does not mean what something is worth today. Present value usually refers to what something is worth earlier in time. So if you have money that's going to be received 10 years from now, and you want to know what it's worth today, you're finding its present value. But if you have money that's going to be received 10 years from today, and you want to find out what it's worth 5 years from today, that is also trying to find its present value, because you're trying to find out what that cash flow is worth in an earlier point in time. You're moving it from year 10 to year 5. Future value refers to what something is worth later in time. So if you have an amount of money in a bank today and you want to know what that's worth 5 years from now, you're looking for its future value. But it's also future value if you say you put money into a bank 5 years ago and you want to find out what it's worth today. Even though technically you want to find out what it's worth at the present time, you're trying to find its future value because today is later than 5 years ago. So the punchline, folks, before I get everyone more confused, is just this. If you're trying to push cash flows forward in time to find out what they're worth later, you're finding the future value. If you're pulling cash flows backwards in time, then you're trying to find their present value. A couple other things. If you see payment or a payment button or the concept or term annuity, that's referring to a recurring sequence of identical cash flow. So think of a car loan or a mortgage payment. You're making the same monthly payment due the same time each period for a large number of periods. And so what that means is that we could take shortcuts. So instead of trying to find the present value or the future value of each of the 36 monthly payments, we can just use an annuity or payment function on our calculator and solve it all at once. And then two other terms that we have to know for starters. One is the number of periods. And so it will be obvious that for the simpler problems that you're going to make 10 payments. So there's going to be n is going to be 10. Or you're going to have something in an account for 5 years, so n is going to be 5. But it will get more complex in a subsequent presentation, or perhaps later in this one, when you have, for example, 30 years, but you have 12 payments per year. So that corresponds to 360 periods, and period would be defined as a month, for example. And then finally, the interest rate. And the interest rate is usually quoted on an annual basis. Interest rate would be 8% per year or 5% per year for the savings rate or for the rate that you would pay on your loan. And again, this will get more complicated as we add sophistication and things like monthly payments or monthly compounding is what it's called. Again, most of the time I'm going to be using either Excel or time value of money calculators, but note that there are formulas for each of these. So to find the future value of something, you just take what it's worth at the earlier point in time, times 1 plus the interest rate raised to the nth power, the number of periods. To find the present value, you take what something is worth later in time, divide by 1 plus the interest rate raised to the nth power. So notice in every single one of these problems, just looking at these formulas can give us a headache, right? But it's the same set of variables that we just covered on the prior slide. You always have a future value, a present value, an I, an N, or sometimes you have payment if there's an annuity. And then this would refer to the future value of that annuity or the present value of that annuity. So sometimes you see other things like CF, that just refers to cash flow. And then this is something that we'll talk about later. Whenever you have an interest rate where you're being paid more frequently than annual, then the effective rate that you'll earn on that account is going to be a little bit higher than the quoted rate. I'll just give you a quick example. Let's say that you put your money in an account that pays 10% per year. Well, if you start off with $100, you'll have $110 left at the end of the year. But what if, instead of paying 10% at the end of the year, your bank pays you 5% for the first 6 months and then 5% for the second 6 months? Well, you'll earn a 5% rate of interest during the first 6 months, so that during the second 6 months, you'll earn 5% not only on the original 100, but also on the $5 of interest that you got paid over 6 months. So you'll end up with a little bit more than $110 because that extra 25 cents of interest was compounded off of the interest that you were paid the first 6 months. So the effective rate on that account, because it was paid every 6 months, is a shade higher than 10%. So that's something that we'll talk about either at the end of this presentation or perhaps at the beginning of the next one, depending upon how far we get. So the best way to learn about these problems is to actually go through a bunch of them. So that's what we're going to do over the next, I've got like 7 or 8 of these to talk through. So for the first example, and you're going to want to get some medication and some caffeine, perhaps even some prescription medication for the next half hour, 45 minutes. So we're going to just be doing problem after problem after problem. So load up. All right, here we go. So first problem, this example is finding the future value of a lump sum. So right there we know that we have a sum of money at some earlier point of time, and we want to find out what it's worth later given a certain amount of time periods and the interest rate that's paid in the account. So in this case, you got a savings account with $100 on your first birthday. It earns 5% per year. You want to find out how much you're going to have on your 21st birthday if you don't take any money out. So the timeline on this should be pretty simple to do in your head. First birthday, 21st birthday. But if you think about it, what does that then translate to for the number of periods that this spans? I'm sure I didn't draw the correct number of lines, but you get the drift. N is going to be equal to 20. First birthday until your 21st birthday. I is going to correspond to 5% interest per year. How about the $100? So we've taken care of I. We've taken care of N by comparing your first birthday with your 21st birthday. So notice we're pushing the cash forward 20 years to find out what it's worth. What's the $100 refer to? Well, I'm going to draw it here because that's what we have right now. So this refers to what it is worth at an earlier point in time. So we have its present value, so to speak. We are then looking for what it's worth at a later point in time. Well, how about the last button on your calculator, or the term that we didn't talk about yet for this problem, the annuity payment? It's irrelevant in this problem. This does not have a situation where you have a sequence of equal payments. If the problem said your parents are putting $100 in on each birthday for 20 years, then we would have an annuity. Not yet. In this case, you have $100 in year 1, and you want to find out if you just left it alone and did nothing else, what that would be worth in year 21. So we have the problem, we've identified it. We've also identified the variables. Now we can figure out the method that we want to employ to solve the problem. Again, Excel calculator, algebra, tables, whatever. So in this case, algebra can work pretty simply using the formula that we covered a couple minutes ago. Future value would be equal to present value times 1 plus I raised to the nth power. So we could put 100 times 1 plus, notice I'm putting it in here as a decimal place. Whenever we use algebra, we have to be careful about how we put in rates. They should be in decimal format. 5%, 0.05, raised to the 20th power. And that's going to give us our answer. Of course, it's kind of a pain to remember how to do all these pieces and orders of operations. Inside the parentheses goes first, so 1.05 raised to the 20th power times 100. So next in order of operations, we want to bring the 1.05, we want to raise that to the 20th power. And to do that on our calculator, we want to use the y to the x button. Will help. So I'm going to plug in 1.05. I'm going to find the y to the x button. I'm going to hit the y to the x button. Then I'm going to press in 20 equals sign. And we're going to end up with let's call it 2.66. Little rounding's okay. And we still have to multiply that by 100. And when we do that, we end up with about 265.3. Ish. So we solved this one algebraically. We've got an answer. What does that answer mean? Look back at the problem. Does it make sense? I'm going to deposit, or my parents are going to deposit $100 on my first birthday. It earns about 5% per year. On the 21st birthday, it'll be worth $265.30. Another way to solve it, to check our work. We have our variables, N, I, PV, and FV. I find the financial functions on my time value of money calculator. It's usually in a row. So I'm going to plug them in. You plug the number in first, and then click the dot. So I'm going to punch 20, then hit N. Then I'm going to punch 5, not 0.05, 5. And then I'm going to punch I/Y on my calculator. Then I'm going to punch 100, and then hit PV. And then now I want to solve for FV. So there should be a button on your calculator. CPT, compute. So you're telling your calculator to solve for something. So I'm going to hit CPT, and then I'm going to hit FV, because that's what I want it to compute. And lo and behold, I get my 265.3. So right now, you're still listening to me because your calculator spit out at you 265.3 and the world is good. Or you've stopped listening to me because you're trying to punch it in again and you're trying to figure out what's up with your calculator because you think you did everything right. Know this, is that different calculators are a little quirky. And so the most common mistakes that will cause your calculator to throw the wrong answer out at you. Number one, the default I/Y setting on calculators or apps, if you buy them, sometimes is set to 12, which means that your calculator is assuming that interest is being paid monthly. And so if that's the case, when you punch in 20, it assumes that that $100 is in the account for 20 months and not 20 years. And so you need to change that default I/Y setting. And to do that, normally you hit the second button on your calculator. So to change that setting, And for those of you who, by the way, it's automatically or already set to 1, it's a good idea to try this because there will be other problems coming up either in this presentation or subsequent presentations where we're going to modify this because we have monthly loans or monthly interest that's paid. And so get out your calculators and try it. So to change the periodicity, you hit the second button and then you hit the I/Y button. And when you hit that, you should see on your screen, it should say P/Y equals, and that's what your calculator is set to. For now, you want it set to 1. So punch 1 and then enter, and it should set to 1. If not, try it again. Okay, so if your calculator is not set to 1 period per year, you want to set it to 1 period per year for the rest of these problems. If your calculator is already set to 1 period per year, leave it. And hopefully you got the right answer. If you did not get the right answer, then there's a couple of other possibilities. So number 1 mistake is the default I/Y setting is off. Number 2, most common mistake is that if you're using a calculator that you borrowed from somebody else or using it and you've done problems on this previously or played around with it, the one thing that you want to make sure is that, remember, we didn't put anything into that payment key because that was irrelevant for this problem. But your calculator remembers the last value that was in that button for a prior problem until you change it. So what you want to do is redo the problem and plug in 0, then press payment. Because again, there is no annuity in this problem. And so those are the 2 most common mistakes that involve a calculator setting that would cause you to get the wrong answer, even though you plugged in the right variables. If that didn't happen, then something else is going on. Try it a couple more times and maybe look at your calculator's tutorial. Another thing that you may have noticed is that actually when you computed FV, your calculator didn't give you 265.3, it actually gave you negative 265.3. And the reason is, if you're using a typical calculator, it gave you a negative 265.3. And the reason is because your calculator assumes that if you're putting money into an account at the beginning, then you're taking it out at the end. So it's going to be in the opposite direction as the cash flow that you plugged in previously. If we had entered a negative 100 for present value, then our calculator would have given us a plus 265 at the end. Whatever. I want to make sure that you understand that the most important thing is being able to interpret the answer and the problem correctly. If you're putting 100 in the bank, you will have 265.3 at the end. It will be important to understand the pluses and the minuses in subsequent problems when we have more complex issues and we'll have inflows and outflows, and we want to make sure they're in the right direction. So far, so good. Okay, on to the next one. So in this case, you'll see we're looking to find the present value of a lump sum. And from here on in, I'm not going to use the algebra. I'm going to be using financial calculator. It's a little bit faster. In this case, we're expected to receive $100,000 in 8 years. You can draw out our timeline. We know that we've got $100,000 coming 8 years from now. We know that the rate is 10% per year, and we want to know what it's worth at period 0. So we're going to be pulling that cash flow back in time to find out what it's worth today. So the first question that I have is the number going to be higher or lower than 100,000? What you want to be thinking about is, let's take a look at the previous example again. kind of a mess now. In this case, at the end of the day, we invested 100 today or in a year, and we had an account that was worth $265 20 years from now. So as long as you have a positive interest rate, money will grow over time. Looking back at this problem, another way to think about it is, what's that worth you today? It's going to be worth less because that amount can be invested and grow to $100,000 over the course of the next 8 years. But let's identify the variables. I is pretty straightforward. That's going to be 10%. N relates to the number of periods, in this case years, that the cash flow is moving through time. 1, 2, 3, 4, 5, 6, 7, 8 years. And 3 other variables that we typically look at: payment, FV, and PV. The 100,000 is what we have later. We're looking for the present value, and payment is again not applicable in this case. So now we want to plug this into our financial calculators. Again, the assumption is going to be that your calculator is set to 1 period per year. Notice your interest is paid annually, so that matches up. That's why we do that. So we plug in 100,000, hit FV, 8, hit N, 10, press I. Again, not 0.1, but the number 10. And for these, it doesn't matter which order you go in. I'm going to put in 0 for payment just because I wasn't sure what was in there from a previous problem. And then I'm going to compute PV. And end up with 46,650.74. So that's the value of your inheritance today. Makes sense. It's going to grow by 10% per year, and over the course of 8 years, it'll roughly double in size. So we've now learned how to solve 2 different types of problems: future value of a single sum of money, present value of a single sum of money. Okay, let's look at a problem where we have to determine what interest rate you are paying or earning. In this case, you've got 2960.4 today. You want to have 5,000 4 years from now, and you're looking for a bank that's going to pay an interest rate that allows you to achieve that result. Of course, this could be a mutual fund or a hedge fund or a private equity fund, okay? You can see something that turns $3,000 into $5,000 in 4 years. It's unlikely that it's going to be a bank that pays 2 or 3%, but no matter. Let's continue. So we've got a timeline. You know it's going to be 4 years. Got it? 2960.4 today. In 4 years, our goal is 5,000. The unknown is I. So let's look at our variables again. We've got present value, future value, I, and payment. Again, payment doesn't matter here, it doesn't exist. Present value, that's the earlier cash flow, 2960.40. Future value, 5,000. I, that's what we're looking for. What interest rate must the bank pay? N corresponds to the number of periods that the interest is being paid. In this case, 4 years. So now we have what to plug in. So I'm going to plug in 2960.4 and hit PV, 5,000 and hit FV, 4 and hit N, and then I'm going to push compute I. Now, if you did what I just suggested, your calculator is going to give you an error, something like this. Looks like error 5 or something like that. What your calculator is trying to tell you is not, you don't have error 5, you have error S. You have a sign error, okay? Your calculator is saying to you, the way that you entered this in is a plus 2960 here, and then a plus 5,000 there, and that's an impossible rate of return. For example, you're telling your calculator you're receiving $2,900 today, and you're also receiving $5,000 in year 4. So you've never technically invested any money. So what we need to do is fix that and tell our calculator, really, we've put in $2,960 to the bank, and we're going to be taking out $5,000 in year 4. Whatever. You got to make one of the cash flows, either present value or future value, negative. So let's do it again. So now I'm going to punch in. So now I want my PV to be minus 2960. So I'm going to press 2960.4. To make that negative, I find and then hit the plus minus button. So now on my screen, it reads minus 2960.4. Now I press PV. So now my present value reads minus 2960.4. Now I plug in 5,000 for FV. Now I plug in 4 for N, then compute I, and I get something around 14%. So the interest rate that I need to achieve in order to get 5,000 out of my $3,000 investment for 4 years is 14% per year, which is either, in this day and age when banks pay 1%, it's going to be a real challenge. But it's probably not going to be a bank. It's going to be a different type of investment. That's for another day. So now we've accomplished 3 objectives: future value of a lump sum, present value of a lump sum, and finding the interest rate. Next one, you have a sum of money, you have a goal, you know the interest rate that you're going to earn, and you want to find out how long it's going to take for you to achieve that goal. So in this case, we're going to need $20,000 for a down payment. You currently have $5,000 in an account that's earning 4%. How long will it take for that $5,000 to grow to $20,000? So again, you probably don't need a timeline at this point. You draw it out anyway. You got $5,000 today, $20,000. And what do I put in for N? I don't know. That's what we're trying to find. And I know that we're earning 4% per year. So let's draw our buttons here: present value, future value, I, and N. Like the last one of these has to enter in as a negative. So I'm going to put my present value in as a negative. I'm going to deposit 5,000 in the bank. At some point, I'm going to be able to withdraw 20,000. I know my interest rate is 4%, and I'm trying to figure out what N is. So 5,000, hit the plus minus button, then PV. 20,000, hit FV. 4, hit I, and then compute N. And N is going to be 35.3. So how would we interpret that answer? It will take you about 35 years for that $5,000 to grow to 20 at 4% interest per year. Long time. So let's say you don't want to wait that long. So what you want to do is you want to try to find a mutual fund out there. It might be a little risky, but on average it might earn 8% per year. So I'm changing the problem, and I'm going to change I to 8 and then recalculate what N is. To do this, you don't need to plug everything back in. You need only press 8I and then compute N. $18 years. So when you have your financial calculator, you don't have to plug everything back in again if you don't want to. It will save minus 5,000 for present value and 20,000 for future value in the calculator's registers. Okay, so now we've done a few problems. Let's do one that uses the payment button. All right. So in this case, we're going to find the future value of annuity. Let's go a little faster. We're going to put aside some money, college expenses. So starting at year 1, each year thereafter to year 18. So right there, we know that we're going to start in year 1 and we're going to stop in year 18. You're going to put $500 into the account, and it's going to pay 6% per year, and you want to know how much will there be in the account over that horizon. Okay, so let's draw the timeline for this one. You can see what creates the annuity here is the $500 is being put in each year. Now, one thing that we could do is we could create a bunch of separate future value of a lump sum problems and say, okay, the first $500 that you put in year 1, what's that going to be worth in year 18? Then you have another one that you put in year 2 and could find out what that's worth in year 18, and so on. That's a lot of different future value problems. So instead, our calculator and Excel and future value of an annuity formula helps us. So in this case, starting in year 1, we're setting aside $500 each year. One kind of weird thing to recognize is that in year 18, just on her 18th birthday, you're putting $500 into the account, and then the day after, you're figuring out what that's worth. So it's kind of odd to think about setting up a timeline where you're putting money in on the 18th birthday and then trying to figure out what that is. But that's how the presumption and standard of these problems work. So if you think about this, let's continue. Let's put our buttons down. PV, FV, NI, and payment. This time we actually have an annuity, $500 that occurs 18 times. Year 1, year 2, year 3, and so on, including year 18. So N is going to be 18. I we have at 6%. What about present value and future value? But one of these we're going to be solving for. How much will there be in the account on, I should read her, 18th birthday? So we're going to be finding the future value. How about present value? That's going to be 0. We don't have anything today put into the account. If the problem was different and said you start with $2,000, then you put $500 per month in, then we would have a present value to plug in. But in this case, we've got 0. So turning now to our calculator, I'm actually going to enter them in just like this. I'm going to put 0 for PV. That way it doesn't remember something from the previous problem when we plugged in minus 5,000. So again, 0 for PV, 18 is going to be N, 6 will be I, 500, then payment, then compute FV, and we end up with 15,452.83. All right, so $500 per year, growing at 6% per year. You'll end up with just over $15,000 18 years from now. Okay, what haven't we done yet? Well, we've solved for PV, future value of a lump sum, present value of a lump sum. We found I, we found N. We've done a problem that involves an annuity. What else have we got? How about an uneven set of cash flows? So in this case, there's a few different ways to solve these, depending upon the process you want to use. The first thing that you want to recognize, the most important thing, is that this is not an annuity stream. An annuity stream is a constant stream of cash flows. And even though these occur evenly a year apart, they are not identical in size. So you can't use the payment button. So we have our timeline. That's an ugly looking timeline. That's okay. 300 in year 0, 400 in year 1, 150 in year 2, and 200 in year 3. And what's the goal? The goal is to figure out what all of those are worth collectively today. So the reason why I put this in here is because I want you to understand the concept that to find out what a stream of cash flows is worth today, it's worth the sum of the present values of each of the component parts. So we have to find the present value of each of the 4 cash flows. So let's go one at a time. Let's erase this. What is this $400 going to be worth today? How do we solve that problem? Well, we know that future value is 400. N is 1, because we're pulling this back 1 year to find out what it's worth today. I, the interest rate is 7%. Present value is what we're solving for. So when we plug those things in, go ahead and do it. You should get 373.83. 373.83. So how about this $150? What's this worth today? Well, we know it's worth 152 years from now, but we're pulling it back 2 years to find out what it's worth today. Solving for its present value yields 131.02. Finally, or year 3 cash flow, future value is 200, n is equal to 3, I is equal to 7. Finding the present value. And again, when you're going through this, if you find something different or you have an error, just remember to clear out your registers, plug in 0 for payment. This one, you should get 163.26. We didn't do this one. What's the present value of this 300? What's this worth today? Well, it's already in today's dollars, so we don't have to do anything to it. If you did happen to enter in future value as 300, n equals 0, I equals 7, and solve for present value, you'll just get back to 300 anyway. So now what we have represents what each of these cash flows is worth today. But we want to know the total, so we need to add them up. So 300 plus 373.83 plus 131.02 plus 163.26 gives us 968.11. And that's our final answer. So somebody offers you a stream of cash flows, $300 today, $400 in a year, $150, then $200. Or if that's a project that you're considering, and that's what those cash flows are going to look like, how much is that project worth to you today? Just under $1,000. You should know that there's an easier way to do this. Again, the focus on this problem was the concept of the present value of a stream is worth the sum of the present values of the parts. If this was given to you in Excel format, there's something called an NPV function where you just type in equals NPV, begin parentheses, 7% would be the first variable in the field, comma, and then you'd highlight the cash flows that start in year 1. So whatever that would be, B2, call it to B4, or wherever these cash flows occurred in the worksheet. And that gives you the value of the future sets of cash flows, and then of course you'd have to add the first set, or the first cash flow of 300. So much easier way to do it in Excel. In your calculator, if you want to play with the CF button, you want to look that up in your calculator's handbook. It's something that we'll do in a subsequent presentation perhaps, but it's another way of entering in the cash flows one at a time and then calculating the present value once. It's a little bit easier. But again, the law will get to 968.11. Okay, we're getting there. In this case, you're borrowing $300,000. You're going to pay. You're borrowing it from your uncle. Going to pay him in equal installments over the next 20 years, and deciding whether to charge you interest. And so, my question to you is, how much do you care? If he charges you no interest, what will your payments be? That'll be simple. But if he charges you 3% interest, what will your payments be? 3% is more realistic. But hey, he's a relative. He's a family member. Maybe he'll cut you a break. All right. So what happens here? Well, we've got 20 years. You're going to start paying back 1 year from now. Okay. So at the end of year 1. So n is going to be 20. Let's start off with 0 for now. We know that you're borrowing $300,000, so you get $300,000 today. You're going to turn around and buy a house with it, but you still get $300,000 at the beginning, and you're going to pay it down to zero at the end. So it's going to be worth nothing at the end. You're paying the loan off. And you're trying to find what that payment is. So let's plug these in. So 20 is N, 0 for I, 300,000 is present value, 0 is future value, and you're going to compute payment. And not surprisingly, two things that you notice. One is that your calculator spits at you a negative number. Of course, you're going to be making payments. You borrowed, you got $300,000 in today that you then went and spent, but whatever, you got it from the loan, and so you're going to be making payments. So this is going to be a negative. And of course, with zero interest rate, each payment is just going to be $300,000 divided by 20. So the next question is, what if the interest rate is 3%? How much will that change your payment by? Again, you don't have to enter everything in. You can if you want to, but I'm just going to plug in 3 for I and then compute payment. Your payment's going to be $20,164.71. So you can see with just a 3% rate of interest, the payment's going to change by quite a bit. Again, most mortgages are monthly, so we'll get to that in a little while or next time. But even a small rate of interest is going to matter. Okay, let's figure out how this works. Let's understand what happens with most loans. There are two different types of loans that companies and people use to borrow. One of them is called a bullet loan, and that's typical for companies, where if a company borrows $1 million, so they get $1 million today, the company usually just pays the interest on that million until that bond matures. Then they repay the $1 million at the end of the bond's life. But in personal finance, that's not how it works. The borrowing or loan, so let's say you take out a loan for $500,000, is paid off over time to a balance of 0. And $500,000 looks like a house, so that would be over a period of 10, 15, 20, or 30 years. What that means is that where a company only pays typically interest each year and then pays off the entire million at the end, personal finance, the loan gets paid off over time. So there's interest and principal that gets paid each month, so that by the end of the loan's horizon, it's paid down. So let's take this example. So in this case, you've got a loan of $5,000. It needs to be paid off in 3 years, making 3 annual payments. Interest rate on the loan is $5,000, and you're going to pay it off fully over time. So how does this occur? Well, we know a couple things. We know that at the very beginning, the loan balance is $5,000. Got it. We know at the very end, the loan balance is going to be 0. We're just trying to figure out what happens in each period. Do things get paid off evenly? Well, not quite. We know that what's typical is that the payments are equivalent. We have an annuity. So, for example, let's figure out what the payments are. We have a loan today of $5,000. We know that that loan is going to be paid off, future value of 0. We know that we're making 3 identical payments, and we know that the interest rate is going to be 7% or 7. When we compute the payment on that, we know that we're going to be making 3 equal payments of, well, let's see, $5,000 present value, 0 for future value, 3 is N, 7 is I. Compute payment, we get 1905.26. 1905.26. And that's an annuity, so we know that that 1905.26 will represent an equal stream of what we're paying over time. Okay, so now we got to try to figure out how this thing works. So this worksheet's a bit of a mess, so bear with me, because you're seeing the entire worksheet when really I want to just show you things one piece at a time. So for example, the loan is $5,000 at the very beginning of its life. We know that the interest rate that first year is 7%. So how much interest will you owe at the end of the first year? Well, $5,000 times 7% amounts to $350 of interest that first year. Again, that's 7% times our beginning balance of $5,000. That's the rent on the money. Hey, you owe $5,000. The bank's charging 7% of that $5,000. That's $350. But remember, you're making a payment of 1905.26. So of that 1905.26, 350 will cover the interest. So how much of the principal is reduced? It's going to be the remainder. So 1905.26 minus the $350 of interest means that you're paying the loan down that first year by 55.26. So the ending balance of your loan at the end of the first year is going to be 3444.74. Okay, so thinking about the first year in total, you start the loan out as $5,000, you make a payment of $1905, 350 of it covers the interest, therefore the principal is reduced by $1555. By the end of the year, you now owe $3444.74. That carries down because that's now your beginning balance in the second year. Notice we are amortizing the loan. The balance is going down over time. So the payment doesn't change, but notice the interest changes because now how much are you renting from the bank? You're only renting the loan balance of $3444.74. So $3444.74 times an interest rate of 7% means that the bank is going to charge you $241.13, and that's 7% of the beginning balance for that year. So your payment is still $1905.26. So now you know that you're paying less in interest, you're paying more principal down. And for year 2, that's going to amount to $1664.13. How did I get that again? You're making a payment of $1905, $241 is interest, therefore the remainder goes to principal. So now what's the balance at the end of the year? Well, take the balance at the beginning of the year and net off what you paid for principal. So $3444.74 minus $1664.13 now gives us an ending balance at the end of year 2 of $1780.61. That carries over. That's our beginning balance in year 3. So what interest is going to be charged by the bank for year 3? Well, how much have you borrowed from them? Well, it started off at $5,000, but now the balance is only $1780.61. So $1780.61 times our 7% interest rate means that the bank's only going to charge us $124.64 of interest that third year. We're still making a payment of $1905. Therefore, the principal will be reduced by $1780.62. There's a little rounding here. And notice that the beginning balance is $1,780. You're paying down $1,780. Ending balance is 0. So we don't really care about the totals much, but it is useful to think about the fact that you borrowed $5,000. The total amount that you paid over time is going to be $1,905.26 times 3. You're making 3 of those payments. So your total payments are going to be $57.15. And of course, that's going to be broken down between a principal of $5,000 and interest of $715.78. So when you're borrowing money to buy a house or buy a car, you'll get a breakdown from the bank, and it'll essentially say, yeah, you're borrowing $5,000. Your total payments will be $57.15. Of that, 700 and some odd will be interest. Of course, if this is a house, the amount of interest that you pay will exceed the principal that you pay, or it'll come close. But this is a loan amortization problem, and it represents how loans get paid down over time and the breakdown between the principal and the interest. So here's a more comprehensive example that involves a house. I don't know if we're going to do this whole thing, but let's take a look at all the pieces. Okay, this is a more advanced, more complex problem. It encompasses a few of the principles that we already talked about and a couple of new ones. So let's take a look. You got a home that you want to buy. The price is $400,000. You got a 20% down payment. Well, that's just code for you're going to put $80,000 down cash, and you're going to borrow $300,000. So we're really talking about the loan of $320,000 here. That's the mortgage that you're going to get. You're going to get a $320,000 mortgage. You're going to pay it off over 20 years. In this case, we have monthly payments, and the bank is charging you 4% interest. That 4% quote is not a monthly quote. They're not charging you 48% a year. They're charging you 4% per year, but you make monthly payments. So right now, you can see that we've kind of got a matching problem, that we've got an annual rate and a monthly payment. So we're going to have to muck around with the variables that we've got and figure out what to do. So let's go step by step. Step 1, what's our monthly payment? Okay, well, let's see if we can't figure this out. Present value, future value, N-I, payment. We're looking for monthly payments, so that's what we don't know. We know that today we're going to borrow $320,000, and we're going to pay it down to 0 over 20 years, and we know that our interest rate is 4% per year. Now, we're going to pay it down over a period of 20 years, but because we're making monthly payments, we have to adapt N to correspond to the monthly payments. Simpler question, how many monthly payments are you making? 20 years, 12 payments per year, corresponds to 240 monthly payments. But now we've got a matching problem because the periodicity, monthly, doesn't match the interest rate that we're going to plug in. So we've got to trick our calculator into thinking that we're making a different interest rate than we are. There's actually one way to do it by changing the setting on our calculator, which we can do. I find it easier to just take the 4% and convert that to a monthly rate. So in this case, if I just asked you what's the monthly rate that you're paying, you're making a monthly rate of 0.33%. So now we've got everything that matches. Our N is number of months, and our I is a monthly rate, and our payment will be a monthly payment. PV and FV are not affected because they represent just what things are worth at the beginning or at the end. So now we can plug these into our calculator. So we're going to plug in 320,000 for present value, 0 for future value, 240 for N, and we're going to plug in 0.33 for I. Not 0.0033, just 0.33. We're paying 1/3% per month. And when we compute our payment, we end up with 1932 point, let's round up to 40 cents. The other way to do this, I'm going to put this down here in a corner because it's not a method that I'm going to use that often, is we can change our calculator settings. Remember that P/Y? Change that to 12. And if we change that to 12, then we can leave I at 4%. So here are your two choices. You can leave your calculator as is and divide the interest rate, or you can change your calculator setting and leave your interest rate as is. Either way, you're making one adjustment. I find it easier just to make the calculation adjustment to I. Try it both ways, or just use the way that I employed and leave it at that. Notice how simple it was. How many monthly payments are you making? 240. Got it. What's your monthly interest rate? Well, I know my annual rate's 4, so my monthly rate is 0.33. Done. Notice also, this passes the smell test. You know, it's a $320,000 loan. It sounds like about $1,900 per month. So that's the answer to part 1. That's my monthly payment. So let's go through, let's go through the beginning part of an amortization table, maybe not the whole thing. I'm not going to worry too much about 2, 3, and 4. Let's just talk about an amortization of this loan for the first year. So let's create a little amortization table. I know at the beginning of the first year, the balance of the loan is going to be $300,000. I know my monthly payment, beginning balance, payment, is going to be $1932.40. How much of that gets dedicated to interest? Well, in this case, I've got a $320,000 mortgage. I know that during the year, I will pay $320,000. This is just space for calculation down here, times 4% during the year. So I know the interest will be about $12,800, but that's annualized. So I've got to divide it by 12 to get that first month's worth of interest. 1,066.67. So the amount of interest that's chunked into that first payment is a shade over $1,000. So how much gets applied to principal during that first month? Well, I made a payment of $1,900. $1,000 goes to interest, so I know it should be around, maybe $900. But let's do the math. 1932.4 minus 1066.67 gives me 865.73. Goes to show you, you borrow $300,000, you make a $2,000 payment, half of it's going to interest. And you can see that about, in this case, $865 and change goes to principal. So your ending balance that first month is going to be 320,000 minus 865.73, 319, 134.27. And of course, that's going to be the beginning balance in month 2. Month 1, and so on. So we could muck around with this amortization table. This type of example is better spelled out in Excel when you can just plug the formulas in and go. But you can see by hand it's a little rote but and repetitive, but it's the concept that's important. I do want to cover the 5th question, the effective rate on the mortgage. Remember, the annual rate is what is quoted to you. That's also called the nominal rate of interest. But because you're making monthly payments, you're effectively paying a little bit more interest. And so you need to convert that to an effective rate. And the formula for that is toward the beginning of this presentation, but it's essentially take the number 1, plus the stated rate of 4% in decimals, because we're using algebra, slice it by the periodicity of the payments, in this case monthly, so slice it by 12, raise that to the 12, and subtract 1. So in this case, our effective rate, again, order of operations matters, so I'm going to take 0.04, divide by 12, I'm going to add 1, and then I'm going to hit the y to the x button to take that, what's in parentheses, to the 12th power, subtract the 1, and I'm going to end up with 0.0407, or 4.07% is the effective rate on the loan. Notice again, it's a shade more than 4%. So work it out on your calculator. It's important to understand the distinction between nominal rates and effective rates when compounding is in effect. It's going to be much different if the compounding frequency is greater or if the interest rate is higher. If the compounding frequency is only something like semi-annual or quarterly, then it's going to make less of a difference. So we've been doing a lot of personal finance examples to illustrate how to solve time value of money problems. Here's an example that involves a company that's borrowing money. So this is a bond sheet, and it's a bond sheet for Appalachian Power Company. And this is a bond that was born or originated back in the 1980s. And like other investments, these things are still sold on the open market. The bond will die or it will mature on February of 2017. So you can see that there's still 4 years left in the bond's life. And they have codes to represent how many of them there are. Each bond has a par value or face value of $1 million. There's other information in the fine print here about what it covers and how you get paid and things like that. It also has a coupon payment of 8 3/4%. In other words, it pays the bearer, whoever holds the security or the instrument or the bond itself. If you lend Appalachian Power Company money, they will pay you 8 3/4% of $1 million each year. In fact, they'll pay you twice a year, but half as much. And so these bonds sell on the open market today each for about 110% of par value. So the question is, hey, if you have to pay $1.1 million and you're only going to get back $1 million in 2017, and these bonds pay you $88,000 a year, what rate of return are you ultimately going to get? And so you can see it's a kind of a complex way to think about things, but let's map it out on a timeline. And to make things a little bit easier, let's create some calibration here and pretend, if you will, that it's August 2010, or sorry, it's August, 2010, and the bond matures in 2017, just like it said on the sheet. And you want to find out what rate of return you'll get if you invest in that bond. So first things first, if you invest in this bond, what are they going to write you for a check each year? Well, remember the coupon payment or the coupon rate on the previous page is 8.75%. So to translate that into a payment size, you multiply that by the bond's face value or par value of $1 million. So in this case, $1 million times 0.0875 gets us to $87,500. So if you invested, if you lend this company money, they're going to pay you $87,500 a year. Except instead of paying you once at the end of the year, they're going to split it in half and make you payments every 6 months of $43,750. So $43,750 in February and $43,750 in August to total your $87,500. So now you can start thinking about a timeline, if you will, of investing in this bond. You know the bond's going to pay its par value or face value at the end of its life in 2017. The bond, you now know, is going to pay you every 6 months $43,750. And what does that look like? Well, that looks a lot like an annuity. Okay, so now we know how much each semi-annual coupon payment will be. $43,750 each 6 months. And we've started to map out a timeline that represents your cash flows if you lend this company money. Now, one of the questions is, well, how much are you going to lend them? And let's say that you end up lending them $1 million today. So out of pocket, you have an outflow of $1 million. You can now see what your anticipated cash inflows will be. If you lend them $1 million and you get in $43,750 every 6 months and $1 million back in 2017, then your rate of return, let's do number 2 down here, will essentially be 8.75%. Except that that's the nominal return. Let's get a little bit more practice calculating the effective return. We know that instead of getting 8.75% per year, you're getting half of that every 6 months. So plugging that into the effective return algebraic formula would yield 0.0875, divide by 2, add 1, square that or raise it to the second power, subtract 1, and we end up with 0.0894 or 8.94%. So you can see again that your effective yield is going to be a shade higher than the stated rate of 8.75% because the company is choosing to pay you interest in effect ahead of time, before the end of the year. So We now know how much each semi-annual coupon payment will be, $43,750. We now know the effective yield if it's priced, if you're lending, or when you buy this bond, you're paying the $1 million face value. But let's say on August 2nd, 2010, the price of the bond is not $1 million. It's 110% of face value. So 110% just means that you're paying 10% above what you're going to get back in 2017. Now, why would you do that? Why would you pay more for a bond that's going to pay you back $1 million? Well, you'll pay more because it's giving you coupons of $43,750 when bonds in 2010 would be giving lower coupons. Another way to think about it is this bond was born in 1987 when interest rates were high. So to be competitive at the time, this bond had to pay coupons of 87 grand and change a year. In 2010, interest rates are much lower. Therefore, if you still own this bond and it's paying coupons at the rate of 8.75%, that's pretty attractive. So the only way that somebody else is going to take that bond away from you or buy it from you is if you charge them a higher price for it. It's an attractive bond. But let's figure out specifically what the new rate of return is for an investor that has to pay a higher price. So for problem 3, let's think about this. We've got PV, FV, I, N, and payment. Okay, let's fix that. The payment. We now know that the payment is the annuity of $43,750. What else do we know? We know that this bond is going to pay off from our timeline above. It's going to pay off $1 million at the end of the bond's life. How many periods will occur between August 2nd and the end of the bond's life? And so now we kind of have to sort of count it out and determine that we've got, we've got 2 per year for effectively 7 years. So N, we're going to put in as 14. What about the rate? Well, and what about present value? Those are the 2 remaining pieces. So we don't put both of them in. We're trying to find one of them. Notice what the question says. What's the bond's yield to maturity? Yield to maturity is code for I, the rate that the bond is paying for a newly investor sum of money. Well, why isn't it just 8.75%? Well, it's different because the new bondholder is going to be paying a higher price for the bond. What are they going to pay? They're going to pay 110% of face value. So the price tag on the bond is $1.1 million, 10% higher than the face value. So let me summarize the situation that we have. We've got an investor that's going to pay, so I'm going to make that an outflow. Present value is negative. Pay $1.1 million for a bond that will pay him back $1 million 7 years from today. In addition, the investor gets $43,750 every 6 months. So the question that remains is, what is the interest rate that that investor is expected to earn? Now we can put it into our financial calculators. So 1,100,000, so 1.1 million, hit the plus minus button because we're investing money. So minus 1.1 million will be present value. 1 million corresponds to the future value. So we're going to plug in 1 million and hit FV. 14 will be N. 43,750 will be payment. And then we're going to compute I. And the I that our calculator spits out at us is compute I 3.46. One thing that we want to remember is look at your n. N is 14. So we know that the periodicity is semi-annual. In other words, there are 14 semi-annual periods in this bond's life remaining as of August 2010. Therefore, the I that your calculator is spitting out at you is a 6-month rate. So to get at least a quick estimate of the annual rate, we can just double it. That's our nominal annual return. That's also known as the bond's yield to maturity, or its YTM. So the punchline, folks, is that this now looks kind of messy. You got a bond that's selling for $1.1 million. It's going to pay you $43,750 every 6 months for 7 years. Then the bond will pay you $1 million. What's your annual rate of return that you can anticipate from that investment? And the answer is 7.92%. Okay, so one more question for this problem. Fast forward a year. So now it's August 2nd, 2011. Bonds similar to this one are yielding 5.84%. So the question is, will that have an impact on the price of this bond? So I want you to think about that for a few minutes first. Does the rate of return that comparable bonds are offering affect the price of this bond? And of course the answer is yes. The price of a comparable instrument will always affect a bond's price. Same as if the price tag of a sporting event goes up, then you can sell your tickets for more. If it goes down, you can sell your tickets for less. Same thing here. So interest rates rise and fall over time. And a year later than problem 3 of this one, yields have come down to 5.84%. So the next question is, what's the price of these bonds? So we need a little bit more space to do this one. So I'm going to just use this blank sheet for a second. So let's think about this from memory. What have we got? We've got a timeline. The bonds still mature in 2017. But in this case, there's only 6 years remaining. Remember, last year there were 7, now there's 6. The bonds still pay $43,750 every 6 months, including when they mature. You also get $1 million at the end of the bond's life. And then what else do we know? We know that rates on similar bonds are 5.84% per year. And what are we trying to find? We're trying to find the bond's price. What will the new price be? So now you can see how making a timeline will assist. In addition, let's write down our variables: PV, FV, N, I, payment. Which one are we trying to find and which ones do we have? We're trying to find the bond's price. What is it worth today? We know the bond's future value, what it's worth or what it pays at the very end. We know that the bonds are going to pay $43,750 every 6 months. So there's our annuity. We know that it's going to pay 12 of those coupon payments or annuity payments. We know that the annual rate is 5.84%, but remember, our rate has to match the periodicity of the payments, which are semi-annual. So we've got to divide that by 2 to get the semi-annual rate. So a little bit more complicated, a little bit more to remember. So our 6-month rate that we want to plug in is 2.92. So now what? Now we plug it into our financial calculators or Excel. 1,000,000 FV, 12 N, 43,750 is our payment. 2.92 is our rate. And we're going to compute FV. I'm sorry, we're going to compute PV and arrive at 1,145,525. In other words, we have to invest. That's where that negative comes in. A shade over 1,000,001 in order to buy these bonds from somebody. So the question to you is, how much will this bond sell for? And the answer is $1,145,525. That's the bond's new price. If interest rates change again, then what happens? Then you put in a different I and you recompute PV. Interest rates change again, what happens? Put in a different I, recompute PV, and so on. And this is what moves bond markets. There are other things too, but this is the primary driver of bond prices. Okay, so we've covered a bunch of time value money problems. There are a couple other ones in this slide deck, and I'm going to give you some time to do them. You can see that this one's a little different, and I want you to spend a little bit of time on this, and we're going to cover this in class, or if people are having trouble with it, I may post the answers online. But let's talk it through for a couple minutes. Start retirement savings on your 31st birthday. You're going to retire at age 60. So picture the timeline in your head. So you're going to save for about 30 years. You're going to make 30 payments of $10,000 into a retirement account. Earns 8% per year. How much will you have in the account when you retire? Then what happens? Then you start drawing down on the account. How much can you draw down each year for the following 30 years, assuming that same 8% rate of return on the remaining balance? And then finally, what happens if you start saving at age 26 and you still retire at the same age of 60 and you still die when you're 90? So work that through and we'll talk about it in class. Finally, I've assigned some homework problems from the textbook. These mirror what's on the syllabus for the course, and time permitting, we'll cover some of them in class. Many of them will look familiar. They'll be like the ones that are covered in this slide deck, but it's good for you to get used to them. There are some tutorials that are associated with some of them that use Excel. I suggest that you use your calculator to try to get the same answer. As always, let me know if you have any questions. I appreciate your time and hope this will ultimately save you more time than it took. And we'll talk soon.